Hey everyone, today I'm going to be solving this question called buildings with an ocean view. And I took a look at the question and I think I have an idea of how I'm going to approach it. I'll quickly talk about my insight and try to implement it. If it ends up being incorrect, we'll look at some of the solutions and try to see what I did wrong. So yeah, that's the format of this video. So let's just get straight into it. Move myself over here. So there are n buildings in a line. You are given an integer array heights of size n that represent the heights of the buildings in the line. The ocean is to the right of the buildings. A building has an ocean view if the building can see the ocean without any obstructions. Formally, a building has an ocean view if all the buildings to its right have a smaller height. So formally, a building has an ocean view if all the views to its right have a smaller height. Return a list of indices, 0 index of buildings that have an ocean view. So let's quickly just draw this out. So we know we have like an ocean here, right? And then we also have buildings. So I mean, the first building will always have an ocean view. But if there's a smaller building behind it, it'll be blocked by that taller building. But if this one's a little bit taller, they'll have an ocean view. If this one's even taller, it'll have an ocean view. And then like ones that are smaller, even if this one's taller than the one to the right. And then finally, something like this. So our goal is to return how many have an ocean view, or the indices. So pretend it's 0, 1, 2, 3, 4, 5, 6, 7. The answer here would be we return 1, we return 4, we return 5, and we return 7. Those are all the ones with a clear ocean view. So one way to approach this question is the brute force way would be for every building, just look to the right and see if there's any taller buildings than you. So we start from this one. We see a taller building, so that doesn't count. We look at this element and we look over to all the elements to our right, and we see that it's the tallest building, so we add it here. Next, we look at 2. We check it. It's not the tallest building. 4 is taller. And then we keep doing that for every single building. We check all the buildings to the right to see if there's any taller buildings. If there isn't any taller buildings, then we add them to the array here. So you can see 4, we look to the right, we see no one's taller, then we add it. For index 5, we see no one's taller, add it. 6, we see this is taller, so we don't add it. 7, you're at the end of the array, so we add it. So how fast is that algorithm? Well, for each element, you're comparing every element to every other. Like for 0, you're pretty much comparing it to all. Like the worst case is you're comparing it to all the other elements in the array. So like you could early stop on the one that's tallest, but pretend you have a situation like this. There's just like one super tall building, right? Let's see. This is the worst case. So pretend if there's one super tall building, for each element, you're gonna have to like look all the way to the end of the array just to notice that something's taller. So that leads to, since I'm dropping the big O, I'm not sure when I'm dropping the big O video, but that leads to an O of n squared complexity. That means like n is the input size, and that means as the input size grows, this grows by a factor of O of n to the squared. Because like pretend we add like another one here, the algorithm will take just that much longer. And yeah, I have a big O video dropping later, but that's O of n squared. So that's a kind of inefficient algorithm. So the way to optimize this algorithm is here. Is actually to start from the back. You see, is to actually start from the element that's closest to the ocean. So we see 7. That has that's like the tallest building we've seen so far. So we add that to our result. Our result. We say that's our result. And then now we know that the tallest building we've seen is over here. Now we pretty much have all we need to maintain is like the max height that we've seen already. So let's do an example here, like an actual legit example. 4 2. Okay, this one is 0 0. This one's kind of a better example. 4 2 1, right? Pretend this is the list, so we say 4 1 2 3, right? Then we have 2. So we have a building of 2 stories. Now we have a building of 3 stories. And then finally we have a building of 1 story. Right? And then this is the ocean view. We have our ocean here. We have our ocean here. So we'll start from the back, and that one always has the ocean view. So we'll store 1. Then we keep track of the max height that we've seen. So the max height here is max equal to 1. Nice. So the max there is equal to 1. The reason why we're storing the max height is because we just care about the tallest building to our right. If we're not taller than the tallest building to our right, then we'll never see the ocean. So we just need to keep track while we're moving from right to left of who the tallest building is. And then for each building, you'll know for sure that you'll know, like, if you're taller than the tallest building, you'll see the ocean view. If you're taller than the tallest building to the right, you'll see the ocean. So yeah, all we need to do is move from right to left, maintaining a maximum, and then comparing ourselves against the maximum. If we're taller than that, we replace the maximum with ourselves. So for example, we start with 1. We move here. Since we're taller than that, we add ourselves. This is 7. We add ourselves here, or like let's give these the indices 0 1 2 3, right? So like we already know that 3 is the very end, so it has an ocean view, and then we store 1 is the maximum. Does 2 have an ocean view? Is it bigger than the maximum? Yeah, it is bigger than the maximum. So we add, so like element 2 is here as well. And then now we say the tallest building we saw to the right is 3. Now we move over to this one. We see that we're not taller than the maximum. And we're not, so we don't need to replace the maximum. And we know we can't see the ocean because we're not taller than the tallest building we've seen on our right. And finally, when we get to 0, we don't even need to look at any of the other ones. We just need to know that the last tallest building was 3, and since I'm taller than that, I should be able to add myself here. And then we get and then we update our max of 4, and then we move over. Pretend there was more here, like something smaller, maybe like 3, right? Then we just compare it against the max, and pretty much. But since we reached the end, we output 320, which is the result here. But it's not in sorted order. So what I would do is I would just literally reverse this array, or just like when I'm developing the result, put it like add it to the resulting thing backwards. And what's the time complexity of this? The time complexity of this would be pretty much O of n. We're just doing one pass. We're moving backwards. So O of n is always faster than O of n squared. Like in a graph, O of n kind of grows like this, while n squared kind of grows like this, not it doesn't taper off that hard, but like kind of goes like this. So obviously we're gonna want O of n operation over O of n squared. So yeah, let me go and implement that, the more optimal solution. One sec, let me wipe my nose. So we have a result here. And like I said, I'm just going to reverse the result at the end. And then for I in range, and I'm gonna go from the back of the array, like I mentioned. So I start at the last element of the array, and I pretty much go backwards, right? And I'll say I'll keep a max value. And I'll start the max value at, you're given an array of integers. What is the value of the, okay, max value equals 0. And now I just go back from the back of the array. Let's go for I in, what I'm going to do, if max, I'll take the, if the heights of the current index, give it a better, it's greater than the max value we see in, result dot append the index. If it's greater, it has to be strictly greater, I think. If, okay, yeah, it has to be greater. Like if I'm just as tall as the building to my right, I can't see it. That makes sense. Then I'll do max value equals else. I think that's it. Just these lines of code will solve you a medium question. Oh. There you have it. That's how you solve that question. Buildings with ocean view, and hopefully my diagram here kind of makes sense. Thank y'all. See y'all in the next video. Stay tuned.